Welcome to the CompTIA A+ Prepcast presented by baremetalcyber.com. Step 2 and Step 3 of the troubleshooting process form the heart of logical analysis and problem validation. Step 2 is where the technician establishes a theory of probable cause based on the information gathered in the first step. Step 3 follows by testing that theory in a safe and controlled way to determine whether it truly explains the problem. These steps prevent wasted effort and ensure that any action taken is based on evidence. In the A+ exam and in real-world support roles, these two steps bridge the gap between observation and solution. The purpose of Step 2 is to brainstorm possible causes of the issue. Technicians use observed symptoms, system behavior, and contextual clues to propose likely explanations. The most basic and common causes should be considered first, as they are often the root of seemingly complex issues. This process helps narrow the field from many possible sources to a focused list of testable hypotheses. Without forming a theory, troubleshooting becomes a series of random guesses rather than a systematic process. Developing multiple theories is often necessary when a problem presents with more than one possible cause. Technicians should consider a full range of factors including hardware malfunctions, software glitches, network misconfigurations, and even user error. While it's important to think broadly, it's equally critical to prioritize based on the context. For example, if a user just updated a driver before a failure, software theories should take precedence. Observational evidence should be used to eliminate theories that don't match what's actually occurring. Past experience and historical data are valuable tools for forming strong theories. Technicians often encounter recurring problems, and drawing on memory or reviewing documentation can provide quick insight. Known issues in specific models, firmware bugs, or software conflicts can be verified through vendor support sites or internal knowledge bases. If a user reports symptoms similar to a previously documented case, that context can fast-track the path to a validated cause. Once a theory has been formed, it's time to test it. Step 3 of the methodology. Testing begins with careful planning. The goal is to validate the theory through non-destructive, reversible actions. Changes that could impact system integrity or user data should not be made until the theory is proven accurate. Safe testing may involve running diagnostics, swapping out components temporarily, or disabling specific features. Always begin with the least invasive test to avoid introducing new problems. Diagnostic tools play a central role in testing theories. Device Manager can indicate driver conflicts or disabled hardware. Memory tests can validate or eliminate RAM as a potential failure point. Ping tests may confirm network reachability, while SMART status checks on hard drives can identify early signs of failure. The outputs of these tools should be compared against known good values to support or reject the working theory. Logging test results creates a useful trail for further analysis. When a theory is proven incorrect, it must be discarded, and the process returns to Step 2. This is not a failure, it's part of the method. Technicians should document each rejected theory and the reason it was ruled out to avoid duplicating effort. It's important to stay objective and avoid becoming attached to any one explanation. The troubleshooting process demands flexibility and discipline, not assumptions or shortcuts. Concrete examples make the theory and test relationship easier to understand. If a system has no video output, one theory might be a faulty display cable. Testing that theory would involve replacing the cable with a known good one. If the internet is slow, a common theory might be DNS misconfiguration, and a simple test is switching to a different DNS provider. For a failed boot sequence, a theory might involve operating system corruption, and testing it could mean booting from recovery media to see if the drive is accessible. In some cases, escalation becomes necessary during Step 3. If the test requires tools, permissions, or actions that are outside the technician's role or access level, the issue must be handed off. For example, if the theory involves a server that the technician is not authorized to modify, escalation to a system administrator is the proper next step. When escalating, it is essential to provide complete documentation of all theories tested, results obtained, and the current status of the system. For more cyber-related content and books, please check out cyberauthor.me. Also, there are other prepcasts on cybersecurity and more at baremetalcyber.com. Testing one theory at a time is essential to avoid confusion about what resolved the issue. When multiple changes are made simultaneously, it becomes difficult to know which one had an effect or whether the issue was accidentally masked instead of solved. Isolating variables by changing only one condition per test allows technicians to draw clear conclusions. This practice not only clarifies the resolution path but also ensures that documentation remains accurate and helpful for future reference or escalation. Iterative testing involves conducting small, controlled tests to gradually eliminate possibilities and narrow the problem scope. This is especially helpful when symptoms are vague or inconsistent. For example, testing one RAM module at a time in a system that fails to boot helps pinpoint which stick may be faulty. Dividing a problem into broader categories, such as hardware versus software or local device versus network, helps streamline the process. In some cases, combining multiple minor tests may be necessary to raise confidence in the final diagnosis. Environmental or user behavior often influences which theory should be tested. High ambient temperatures, dust accumulation, or inadequate power supply can cause problems that appear to be software-related. Observing how a user interacts with a system can also be revealing. If the issue always occurs after a specific action or at a specific time of day, that pattern may point to a root cause. Interviewing users about their habits and routines can uncover contributing factors that are not immediately obvious through system logs or diagnostics. Once a theory is validated, it directly informs the plan of action. The goal of testing is to move from uncertainty to confirmed understanding. With the correct theory confirmed, technicians can confidently proceed to apply a fix, knowing it targets the true source of the issue. This reduces unnecessary effort and prevents changes that introduce new problems. Instead of attempting multiple random fixes, the technician works efficiently with a high probability of success. A variety of tools may be used to confirm or reject a theory, depending on the nature of the suspected cause. Hardware tools like loopback plugs or power supply testers help validate physical components. Software-based tools like Task Manager, event logs, or performance monitors provide visibility into how the system is behaving. Bootable USB drives or recovery environments offer isolated platforms for diagnosing startup issues or malware infections. Using the right tool for the right test enhances accuracy and reduces diagnostic time. Testing incorrect assumptions can have consequences beyond wasting time. Making changes based on the wrong theory may create new problems, disrupt system stability, or result in data loss. For instance, reinstalling the operating system as a first action without evidence could erase user settings or files unnecessarily. This underscores the importance of observation and validation before taking action. Good troubleshooting includes discipline about what not to do, as well as what should be done. Some theories require special caution due to the impact they may have on systems. Replacing hardware, reinstalling the operating system, or editing the Windows registry are all high-impact actions that should be delayed until all other possibilities are exhausted. These actions can fix problems, but they also introduce risks and should only be pursued after less invasive testing has been completed. Having a backup plan in place, such as a recovery image or user data backup, is essential before moving forward with drastic steps. A theory becomes confirmed cause when the problem can be reproduced consistently under known conditions and then eliminated by a specific fix. For example, if a particular USB device causes a blue screen each time it is plugged in, and the issue disappears when the device is removed, the connection is clear. When the applied solution results in the complete disappearance of the symptom, technicians can be confident that they have found the root cause and are ready to proceed with final resolution and verification. Documentation plays a critical supporting role during the theory and testing phases. recording each theory that was proposed, the method of testing, and the result pass or fail creates a timeline of activity. This not only prevents duplicate testing, but also contributes to team knowledge. When patterns emerge, such as recurring failures in the same hardware model or software version, the documentation becomes a resource for proactive measures or vendor discussions. Shared knowledge improves troubleshooting across the organization. To summarize, establishing and testing a theory of cause is at the core of effective troubleshooting. It relies on logic, evidence, and methodical action. Begin with the simplest explanation, use the appropriate tools, and test in a safe and controlled manner. One theory at a time ensures clarity, and confirming the actual cause sets the stage for lasting resolution. Steps 2 and 3 of the 6-step methodology are where critical thinking is applied, and the quality of decisions made here will determine the success of the entire process. Thank you for listening. Please visit baremetalcyber.com for more cybersecurity information, podcasts, books, and more.